All right, my friends, we're going to have a not full class today because we're going to finish up series. And then if you want extra credit, right, you can come out with me to do math on the quad. And I'll tell you what you have to do for the extra credit. It has to do with series. I don't even fucking know what it is yet. So we'll figure it out while I'm talking here. Hopefully my brain will do the processing. We will be meeting normally on Friday. And then our final, let me just say it, let's say it all together, is next Wednesday at 10:10 a.m. Am I right?
Yes.
Yes.
I got it, fine. In this room. I will, yesterday I posted a ridiculous amount of review material for the final. I will also post practice finals for you, so you have a sense of what to expect. And let's do the classic 8.5 by 11 inch note sheet, double-sided, you know, the standard. I guess you can bring a derivative table or integral table if you want. I don't think you're gonna need it. If you know the power rule, you're probably good to go. Okay, cool. So let's finishing up series. So last time we talked about Maclaurin series. And this is really a special form of the general series that we're going to talk about today. But the Maclaurin series says that I can take a function f of x, and provided it's nice enough, I can write it in terms of its values at 0 in the following way. How about an x? So I get to express the function as an infinite polynomial, as a power series. We did this for a couple of things. So we found out that e to the x was 1 plus x squared over 2 factorial, x cubed over 3 factorial. A couple of really beautiful things we found the other day. So that was certainly the nicest one. But we also did sine of x was x cubed over 3 factorial, x to the 5th over 5 factorial. I would have these written down on my note sheet because they make some easy work out of a couple of things. And I'm going to show you what in just a second here. Look at the beautiful rhythms. And once you see them, you never forget them in many ways. And then we proved this result about imaginary numbers and e and cosine and sine, proved Euler's formula. And then the special version of that was that e to the I pi plus 1 equals 0. So that was kind of how we ended things on Wednesday. I'm putting that up again because I don't want you to forget it, because that's too amazing. So, today I want to push this a little further. I think we also showed, we found the natural log series, but let's just leave it go. So today, notice these are all centered at 0. That's what it means to be a Maclaurin series. You're a power series representation of a function that is centered at 0. The general version that allows us to center anywhere is called Taylor series. So this is just, again, a power series representation. So power series representation of a function at an arbitrary center, at a center x equals c. So instead of at 0, and you can look at these series and know that they're power series centered at 0 because it's not x minus something or x plus something that's being raised to various powers. So the formula looks like this. I'll put the general form up in a minute, but we have f of x is f at c plus f prime at c over 1 factorial. Now, this could be, you could think of this as over 0 factorial times x minus c. Check out the difference here. So it looks very similar, except where we're evaluating the derivatives on down the way. Same idea, just a different center. Do you see the rhythm? Could you tell what the next term was from that? Cool, so third derivative over 3 factorial, x minus c cubed. Let's do an example of this. So find the Taylor series expansion of f of x equals sine of x. So now, see, we've got sine of x over there. That's around 0. That's what it looks like at 0. We're going to do this at pi, because that's another happy value for sine. So about x equals pi. So this is my new center. Look at the formula. Look at what the formula requires. So up there we have c equals pi in the formula. I still need to crank out a bunch of derivatives. So step 1 in any Maclaurin or Taylor series, step 1 is get the derivatives if you don't already know the series. So get derivatives of the function. So the first thing here is we got f is sine. I'm just going to write it up. And then f prime is cosine. F double prime is negative sine. And you know how this game goes. If you've played this a lot, you might not ever play it too much more if this is your last math class. I don't want to hear anybody be happy about that. Got all these derivatives. Oop, that's pretty shitty, but you get them. That's of x, of course. So get the derivatives of f, and then evaluate them at center. And here our center is pi. So I'm going to find f of pi and f prime of pi. Down the way. Well, might as well do the fourth one, because that's actually where things start to repeat. Notice how this thing repeats in blocks of 4. I'm already back to where I started, and then this rhythm is going to continue on. So sine of pi is 0. Cosine of pi is negative 1. Sine of pi is 0. Cosine of pi is negative 1, but I got a negative out in front. Ooh, and so that becomes positive 1. Then this is going to be 0. And from here, you can start to see the rhythm. It's going to go 0, minus 1, 0, 1, 0, minus 1, 0, 1. A little chant we could have if we wanted. And there's some sort of transcendental math state. But we're not going to chant it, we're going to use it. So then plug into the formula above. So we are going to have sine of x, that's my f of x, equals f at c, so that's 0. Let me write this up so you can see it. So that's the f at c, minus, so that's the f prime, 1 times x minus pi. So this is f prime at c over 1 factorial. F prime at c was just negative 1. Then the next term, the double prime, is 0, so that's cool. I don't even need to write the other stuff. Plus 1 over, so now I'm at f triple prime, so I have a 3 factorial underneath. Check this out, because this is where things started to change. So this is f triple prime over 3 factorial, and then I'm going to have x minus pi cubed. Let me stop for a second, because I've just been rolling. So jacked up from chalking on the quad. How does that sound? And let me know, is there anything I can clarify there at all? So we have our series, and if we wanted, we could, let's actually leave these up, because we're going to come back to that. I could keep expanding this out. So the trick is get the rhythm from a few terms. Do some basic computations at the beginning. Let me say this really fast, Abraham, first. And then after you see a rhythm, now continue on with that rhythm because it's well established. Yes, sir?
I was just wondering if it would be minus 1 over 3 factorial for that one.
So I'm curious why you're thinking that. Can you explain?
Doesn't it like switch the plus minus? Or
It
no,
does.
Never mind. It just adds them on this one. Sorry, I was thinking of the.
Oh, it's okay.
Alternate.
Is it feeling good now? Okay, awesome. Any other questions? It's a great question. So up here, I could say sine of x is equal to, and I'm just going to continue this rhythm. What's the next term? Love it. Yeah, see that? And then 1 plus 1 over 7 factorial. So once you get the rhythm going, it's pretty straightforward. And then minus plus forevermore. Yes, ma'am.
I've noticed that there's a difference between sine x and sine of x. Can you just explain that real fast? Because like sometimes you put parentheses around the x.
Oh, that's just, yeah, that's more like the style of exclamation point I use,
so
really.
up above, when you have, that's the same thing, sine of x there?
Yes, ma'am. Yeah. That's,
Okay.
Yes. Yeah, I flip back and forth from time to time. Usually, Sophie, if it's pretty clear that the x goes with the sine, I would do that. But if I had like other stuff in there, I would probably definitely do that so that it was clear the of x was with the sine.
Okay.
Yeah, that's a good question. So now I could use this to whatever extent I wanted to approximate values of sine near pi. So remember that this is good in its radius of convergence. So all these series are valid inside the radius of convergence. And I'm going to tell you how to find the radius of convergence in the sweetest, easiest way possible. So like when you get an arbitrary, when you do this process, you know something. You know where the series is coming from. So the way to determine in a Maclaurin series or a Taylor series, I guess I have to erase something here. The radius of convergence is to see if the function is undefined at some point. So if the function blows up or has an asymptote at some point, that's called a singularity. So to find, I just wanted to explain that terminology before I said that. To find the radius of convergence for the let's just say Taylor series, because that includes these, it's just when c equals 0, series of a function. Find the distance from the center to the nearest asymptote, the nearest vertical asymptote. If there's no asymptote, like there is with sine, the radius is infinite. If no asymptote, in other words, the domain of the function is all reals. Domain of f equals all reals. Then the radius of convergence is infinity. And all numbers are good. It's a really helpful little trick. So what I would like to recommend is I'm going to give you a problem to try between now and Friday. And I'd like you to try this, like really try this, because there shouldn't be much homework you have to do besides prepping, right? There's all the web works are closed. And yeah, so what I would like you to do And then we'll start off the hour with this on Friday, where we will be meeting in person. Because I would like you to find the Taylor series for, and this is going to be a nice chill one, you're going to like this, for f of x equals x to the fourth plus x squared plus 1. A nice finite polynomial. So this is actually a power series. This is literally a power series about 0 with a center of 0. It's just like most of the terms are dead. We're going to convert that into a power series around a different point. So find the Taylor series for this of around center x equals 1. Find the whole series. You'll have to like go down to the fourth derivative, fifth derivative maybe. But find the first 4 or 5 derivatives of this thing and literally use that formula that we have over there with c equals 1 for your center. And if you can do that, you're going to be, you understand what's happening. But this is when you can completely have the whole series in front of you. The series will eventually be 0 because eventually the derivatives of this are 0 forever. So let's try that. Let me take a little picture of that so I remember that I told you to do that. And I've got one more thing I want to show you how to build new series. I'm also kind of thinking about having a problem session next week, like on Zoom, something like that, like a little problem session. You can come and ask questions and we can work problems together. I will record it so that everybody has access to it, but basically just prepping for the final. So we're gonna have lots of extra time to prep. Let's get rid of that shit right there. Let me take my picture. Cool. All right, one last thing about series. I can take basic series and make more interesting series from them. So once you have the series, you really have a good sense of what this function is. And you can do calculus with it using the series. You can do arithmetic with it, like adding and subtracting, all that kind of good stuff. So let me just title that here. We can use existing series to find new series. And some of the problems that I've given you to review, make sure to look at this, the ones I said, look at these. I've given you a list of things to look at, like the sheet that I have in front of me. So be sure to check those all out. So for example here, find the series, find the Maclaurin series, so that means it's going to be around 0, for e to the x squared. So this is easy if I know this. What that means is literally, and you can think of this as a little box here. Luckily I'm recording this, so this will be there if you need to come back and see what I'm saying. You can think of that x as a box, because this is a function. And anything I put into that box, I just have to copy over to here. So if I want e to the x squared, I take the e to the x series and replace x with x squared. So replace x with x squared in the e to the x series. And I'm going to get 1 plus x squared squared over 2 factorial plus x squared cubed over 3 factorial on down the way. And I see the rhythm now. And then I would simplify. And so I've got 1 plus x squared plus 1 over 2 factorial x to the 4th plus 1 over 3 factorial x to the 6th. And now that I've got that rhythm, I see what's happening here. It's going to be 1 over 4 factorial x to the 8th for the next one, and so on. So let me ask you this. Can you find the series for e to the negative x? What is that series going to look like? simplify, like get in there, do it, and then simplify it out as much as possible. There's only like a little bit you have to do to simplify. Good, turns into an alternating series. All the odd powers, the negative can be brought out in front, and all the even powers, the negative just goes away. We've got a really beautiful series there. Is this making sense? Yeah, cool. Let's do one more. So what about, let's do something really, really interesting and strange. Let's do the limit as x goes to 0 of sine of x over x, but do it with series. So like in Calc 1, you saw this limit. Does anybody know what that limit is? They like tell you and they don't prove it because it's hard. It's 1. Yeah, so this limit, you learned that this is 1. But let's see it by a series. Look, let's just go down here. So this is lim, so we know the answer is 1, or we just learned that the answer was 1. And we've got the sine series, so it's x minus x cubed, this thing. And we're going to divide that by x. So look what happens. Each of these x's goes down a power. So this turns into limit as x goes to 0 of 1 minus x squared over 3 factorial plus x to the 4th over 5 factorial minus plus forevermore. What do I get when I plug in 0 for x? 1. So I just took a limit using series. And it's actually obvious why that is the limit with series. Let's do another one. I'm going to ask you to do one for me. So you've got these series written down, hopefully. Could you please use series to find this limit? Limit as x goes to 0 of e to the x minus 1 over x. Notice that you can't just plug and chug because e to the 0 is 1, so you get 0 over 0. So use series. Take the e series, subtract 1 from it, divide by x, and find what happens when you plug in 0 for the x. That x got kind of crazy. Bless you. Step 1 is figuring that out. What's the limit? could also use L'Hopital's rule and all that kind of stuff, but we're here, right? We're doing it this way. Let me give you one last example, and then we're gonna go chalk it up. So here's the deal for this chalk thing. If you come do chalk and write anything you've learned this semester on the chalk out there, get me to see it, I'll add 10 points to your final. I mean, or don't, that's cool too. Do as you see fit, bless you. And you can go over 100 with that 10 points. Sometimes I just like cap it, and then like the people who would naturally get 100 don't get any benefit. All right, so last one. What is the Maclaurin series for that? We talked about this, do you remember? What is that the sum of? Looks like sum of an infinite geometric series, right? That's the formula. First term over 1 minus the common ratio. So my first term here is 1. My common ratio is x. So just multiply by x each time. There's a geometric series, right? That's a, if I showed you this and said, what kind of series is that? I hope you'd say geometric. What do we need to have true about the radius for this to converge? So one, I heard 1, yeah, definitely. Less than 1, something with 1. Yeah, less than 1, absolutely. What is the series? So let's just take a chance here, and I kind of went through this quickly last time. Let's just notice this. Let's find that derivative. Well, I'll give you a hint, it's this. So the derivative of that is that. You could check that. I hope so. You're at the end of Calc 2. I hope that could be done, given some time. What is the series expansion for that, Ben? Well, I'll just differentiate that series. So if this is that, then the derivative of this must equal the derivative, so let's put a little must equal the derivative of this series. So 1 over 1 minus x squared. The series representation is 0 plus 1 plus 2x plus 3x squared plus 4x cubed on down the way. Done. I just rocked out a series. What's the radius of, where's the series centered? 0. Where's the nearest singularity? Where's the bad spot for x? What x value? 1. Center's at 0, bad spot at 1. What's the radius of convergence? 1. There you go. Exactly. So here, radius of convergence equals 1. See how nice that is? Like, you don't have to do all the deep analysis that you would if you didn't know anything about the series and you just had it cold like that. You'd have to go through the test that we had to find the radius. All right, that's all I have for you, friends. Good shit. We are going to talk. We'll talk more on Friday, but like that's enough for today. Let's go get some bonus points. I've got some people guarding the chalk out there. They better be out there guarding the chalk. It will be a polynomial, but I want the polynomial that looks like x minus 1. So it'll be different powers. You're going to re-express that polynomial in powers of x minus 1. Yes, so as you go through this process, you will literally get that out. No. Yeah, exactly. 100%. Yeah, it'll be cool. Oh, nice. then who said that?
I'm not doing it.
Oh, you tell your tutor, that's crazy, because we can rewrite the polynomial at a different center.
He just didn't think you were gonna do that, so he was like,
Totally gonna do that. He's wrong, he doesn't know me. Who's this person? This person must not know me. Yes? Oh, beautiful, yeah. But this is good. So this, you're not evaluating these at 0 first, or at 1. So evaluate that at 1, and there. This thing should never have anything other than x minus 1, a single x minus 1 for each coefficient. So, in other words, evaluate this at 1, this at 1, and this at 1, and then put those in.
Okay.
Does that make sense?
Yeah.
Cool.
Real quick,
Yes?
I've got that polynomial that you want us to find, the Taylor series. So if the A is equal to 1 that you specified.
Yes.
We're